All right, it's recording now. Welcome to the Astrocheminar. It's 11 a.m. and we're going to get started. So welcome to this part 2 of the May Astrocheminar. This will be Professor Ralf Kaiser's talk. Unfortunately, we missed him we didn't miss him. The Zoom technical difficulty didn't allow us to listen to his talk. So here we are. Hopefully this time it will all go to plan, and we'll be able to enjoy the full talk. So Professor Ralf Kaiser got his diploma and his PhD from University of Münster in Germany. Then he did a postdoc at the Reaction Dynamics group in University of California, Berkeley from 94 to 97, and spent some time in Academia Sinica in Taiwan, in the Institute of Atomic and Molecular Sciences. Then Dr. Kaiser did his physics habilitation from 97 to 2002. And after that, he joined in 2002 as a professor in University of Hawaii. Currently, Professor Kaiser is the director of W.M. Keck Research Laboratory in astrochemistry. Professor Kaiser is a fellow of the ACS and, of course, a past chair of the astrochemistry subdivision as well. He's also a fellow of AAAS, Institute of Physics, APS, and fellow of the Royal Society. Today, Professor Kaiser is going to talk about an aromatic universe, a physical chemist's perspective. So over to you now, Ralf.
Okay, thank you very much, Pater. I would like to apologize to everyone that you have to log in again, but I hope this time everything will go smoothly. So I will talk today a little bit about polycyclic aromatic hydrocarbons in space and on Earth. So what are polycyclic aromatic hydrocarbons? PAHs are actually hydrocarbons which contain at least 2 fused 6-membered rings, such as here the naphthalene substructure. However, if you have aromatic structures which only contain 6-membered rings, essentially you will sooner or later get 2-dimensional nanostructures such as nanographene layers. So in order to go out of plane for aromatic systems, you have to add 5-membered rings, such as done here for coanolane. So this gives access to 3-dimensional nanostructures. So why are polycyclic aromatic hydrocarbons important? So as we know, on Earth, PAHs are actually considered as unwanted and toxic byproducts in incomplete combustion processes. On the other hand, in deep space, such as in our solar system and in the interstellar medium, polycyclic aromatic hydrocarbons are considered to carry up to 1/3 of the cosmic carbon budget. So it's really important to understand how aromatic substructures are really formed in deep space, to also understand the organic chemistry which is happening in the interstellar medium and in our solar system. There are actually 2 typical examples where PAHs are important. For instance, in our solar system, such as in the atmosphere of Titan, one of Saturn's moon, there you have an aerosol layer, and it's contemplated that aromatic system, besides polyacetylenes and polynitryls, are the dominating component of the organic matter in Titan's atmosphere and the aerosol layers. And these are definitely formed at low temperatures. On the other hand, aromatic compounds such as complex as coronane and coanolane has been detected and known to exist in meteorites for the last 20 years, such as in Murchison. And it's pretty clear that based on the carbon-13 to carbon-12 and D/H ratio, these PAHs are definitely not contaminants from terrestrial contamination processes, but that these aromatic systems were really formed in deep space. So how do the astronomers and planetary scientists think that aromatic subsystems are really formed? So one of the critical theories is that the phenyl radical might be an important intermediate or initiator from the stepwise molecular mass growth processes. So the phenyl radical is thought to react with non-cyclic hydrocarbons to form through stepwise mass growth processes by expansion of 1, 2 rings such as naphthalene, phenanthroine, anthracene, and eventually forming two nanoparticles. Another route is actually that we can form the PAHs, at least the first ring, through resonantly stabilized free radicals, such as propartial radical C3H3. This might go to benzene if it's a third body collision, or to the phenyl radical if it's a bimolecular reaction. So we could also, according to models, bypass the traditional single cycle route by going through a C5H5, so cyclopentadienyl radical self-recombination. This could go directly to naphthalene. So far, these models have been predicted and placed on paper chemistry, but it's really important to really find out what are the real reaction mechanisms to form PAHs. It's pretty clear that the formation of aromatic structures in space is not well understood. This is demonstrated by two critical timescales. One timescale is the timescale which it takes to make or to synthesize aromatic structures. On average, it takes about 2 × 10⁹ years to synthesize or prepare an aromatic substructure in circumstellar envelopes of carbon-rich stars in the outflows. On the other hand, models predict that the lifetime of PAHs in the interstellar medium is only 5 × 10⁸ years. Even for astronomical standards, this is a difference. This means the PAHs are much faster destroyed than formed, so there shouldn't be any aromatic structures, and this is against what has been observed astronomically. So it's pretty clear that the formation of aromatic structures in space has not been understood yet. Either the models are wrong, or reaction mechanisms are missing, or a combination of both. So that's why we started a few years ago a systematic research program to investigate the dynamics and the energetics involved in the formation of polycyclic aromatic hydrocarbons in extreme environments. Extreme environments means at very high temperatures, such as in circumstellar envelopes, where we can have a few thousand Kelvin of carbon stars, or in very low environments, such as in the interstellar medium, where we have typically 10 Kelvin in cold molecular clouds, or in Titan's atmosphere, where we have temperatures of 70 to 100 Kelvin in the relevant layers. And we exploit two distinct methods. One method is the cross-molecular beams approach. I will talk about it later. And the second approach is a chemical microreactor connected to vacuum ultraviolet detection of the products, which is at the advanced light source. So I will talk about 5 fundamental reaction mechanisms, how aromatic molecules can be formed in low temperatures and or high temperatures. Mechanism number 1 deals with the classical mechanism which was originally proposed by Franklach. This is a hydrogen abstraction acetylene addition mechanism. After that, we switched to the hydrogen abstraction vinyl acetylene addition mechanism, which operates at low temperatures. Then we have the methylidene addition cyclization aromatization pathway. Number 4, the phenyl addition dehydrocyclization. And 5, most recently, the radical-radical reactions. So let's start with the classical hydrogen abstraction acetylene addition, which was proposed by Franklach. So Franklach suggested that the phenyl radical reacts with stepwise 2 acetylene molecules to eventually form naphthalene. Over the years, 3 major pathways were actually proposed. First, we have the addition of 1 C2H2 molecule. After that, we have isomerization, addition of a second one. We have an initial addition of a second acetylene molecule, or we can go through phenylacetylene by hydrogen loss. So essentially, we have 3 pathways. So this has been studied on the paper and through electronic structure calculations. But the experiments who really demonstrated this were so far lacking. So we investigated reactions in a paralytic reactor to really prove or disprove the Hacker mechanism. So first we have to generate the reactant, which is the phenyl radical. The phenyl radical we generate by pyrolysis of nitrosobenzene, C6H5NO. We are seeding it at very low concentration of 0.1% typically in helium carrier gas. Here we have a heated silicon carbide tube up to 1100 to 1500 Kelvin. So we generate a clean source of phenyl radicals. So these phenyl radicals are reacting then with the acetylene carrier gas in the beam. And this reactor we have integrated at the chemical dynamics beamline at the advanced light source. In detail, the reactor is here in this differentially pumped chamber where we have typically 10 to the minus 4 torr operating. We have a CW source. We have the silicon carbide tube where the beam expands. We form a supersonic expansion. And we interrogate the supersonic beam with a quasi-CW vacuum ultraviolet beam from the advanced light source, which we can tune from about 7 to 11.5 eV. So we can photoionize the reactant products. Then we generate ions, of course, and the ions are analyzed in a reflectron time of flight mode. The nice thing is, since the VUV light is continuously tunable, we can selectively ionize distinct isomers. And we can also plot the intensity of a well-defined ion of the pH of interest versus the photon wavelengths and extract photoionization efficiency curve, as I will show you later. So what did we reveal for the Hacker mechanism? So we reacted the phenyl radical with C2H2 carrier gas, and we detected two critical end products, the phenyl acetylene and the naphthalene. So this proves that we do form naphthalene through the postulated Hacker mechanism, but we still have three sub pathways possible. So in order to elucidate which sub pathway we have, we actually prepared the brominated precursor of the predicted radical, which Franklach predicted. Here we have the 1-bromostyrene radical, and here we have the orthobromostyrene radical. We prepared them in separate experiment and also reacted them with acetylene. And in that case, we saw that we really see the naphthalene molecule to be formed. So we have evidence that these two radical intermediates are critical precursors in the formation of naphthalene by the Hacker mechanism. So the evidence that the Hacker mechanism operates to the formation of naphthalene. The problem is now the following. We have evidence that naphthalene can be formed. However, calculations by Mabel suggest that the Hacker mechanism is actually stuck with the formation of naphthalene. So we might expect on the paper, since we can form from benzene to phenyl to naphthalene, it should be also possible to expand another 6-membered ring. For example, going from naphthalene to phenanthroine and anthracene. This means PAs with 3 rings, such as this guy. However, Mabel predicted computationally that this pathway does not happen at combustion relevant temperatures. Why is this the case? So he predicted once we form naphthalene, if the naphthalene generates a naphthyl radical, if acetylene reacts with the naphthyl radical, it's stuck to the aza naphthalene, and it does not go to phenanthroine or anthracene. So this is so far only on the paper. So we wanted to investigate, is this true that the Hacker doesn't happen, or is there a problem with the theory? So we conducted the experiments. We generated the 1 naphthyl radical and reacted the 1 naphthyl radical in the paralytic reactor with C2H2. And we really form evidence that we only form the aza naphthalene based on the photoionization efficiency curves. We do not form anthracene, we do not form phenanthroine. So we have evidence that the Hacker partially fails, but still, is there any other pathway to form PAs with 3-membered rings such as phenanthroine? So Franklach expanded the original Haka concept. And based on the paper, he suggested, for instance, if we have, let's say, this phenanthrene molecule, if we take out the C2H2, we should be left with a biphenyl molecule. If we have the biphenyl radical, we might have a 4+2 Bay closure process similar to the Haka mechanism. And this we also confirmed experimentally with the advanced light source. We prepared the biphenyl radical, the C12H9 radical from the iodated precursor, and reacted with C2H2 and detected C14H10. And the photoionization efficiency curves makes it clear that this is only phenanthrene, but not anthracene. So this is an isomer selective synthesis of phenanthrene by the Haka mechanism. This also was supported by Alexander Mebel's through electronic structure calculations. We have the biphenyl radical, we have an entrance barrier to addition of the C2H2, we have a ring closure, and we are losing a hydrogen atom from the bridge here, forming aromatization and the aromatic species. The issue here is that the Haka operates with respect to phenanthrene, but it needs high temperatures because we have an entrance barrier to reaction. So how far are we now with the Haka mechanism? So Haka definitely operates very efficiently from the phenyl radical to form naphthalene. And naphthalene goes to azonaphthalene. And we have evidence that we have the biphenyl species, which can generate the biphenyl radical, and we can go to phenanthrene. And in a separate publication, we also investigated that here we can have another 4+2 Bay closure to form the pyrene molecule. So this Haka mechanism actually operates at elevated temperatures. However, as we have seen before, this Haka pathway, which is summarized so far on that slide, does not form anthracene under our experimental conditions. So still some pathways must be missing, which we haven't accounted yet. So this might be pathways without entrance barrier because Haka operates only with entrance barrier at elevated temperatures. So it cannot account for the formation of aromatic systems in cold molecular clouds, but it could account for the classical pathways in circumstellar envelopes. Keep in mind, when we look in these interstellar environments, we still have the discrepancy between the formation times and the destruction times. So one possibility is that we have a so far unknown mechanism to form aromatic systems at very low temperatures, which has not been considered previously, because classically aromatic systems were considered to be formed only at very high temperatures. So this brings us to the second mechanism, which is the hydrogen abstraction vinyl acetylene addition, or the HAVA mechanism. So for that we used cross-molecular beams. This is always an ideal choice if you don't know anything about the reaction dynamics and if you want to figure out new reaction mechanisms. So in this case, for instance, we are generating the phenyl radical, a pulse beam of a phenyl radical by photodissociation of the precursor, like the chlorobenzene precursor. Then the phenyl radical, the supersonic beam, molecules from that beam collide with the second reacted beam, such as the vinyl acetylene. We have a collision. Here, sometimes we form products and they are detected in a triply differentially pumped mass spectrometer. So this is a picture of the machine. So typically the sensitivity is about 5 to 6 ions per laser pulse we can detect. And we have about, so 10 to the minus 23 moles is the detection sensitivity. Here we have our main chamber of the machine. This is a detector which can be rotated. Here we have our primary beam, and the secondary beam comes out perpendicularly here. And this is operated under single collision condition. This means one phenyl radical reacts only with one vinyl acetylene molecule. Then the reaction products are formed and they fly undisturbed away. So we have no secondary reactions. What do we see in these reactions? So we generate the phenyl radical, we react it with vinyl acetylene C4H4, and we detect products at mass to charge 128, so C10H8. Of course, naphthalene can have multiple structural isomers. March 128 is necessary that we might see naphthalene, but we also have to convert the time of flight spectra and the laboratory angular distribution from the laboratory frame to the center of mass frame. We also conducted additional experiments of D5 phenyl radicals to get isotope label studies, so to trace the D versus H atom. And we only detected the H atom emission and the mass to charge at 133. So to make the long story short, the calculations fully support our experimental finding that we have the reaction energy to form the naphthalene molecule. This is a very peculiar reaction because we have the phenyl radical, which reacts with the C4H4, and we form initially a van der Waals complex. And this van der Waals complex, the radical center of the aromatic radical, has long-range bond and in interaction to the CH2 unit of the vinyl acetate molecule, not to the acetylenic unit. Once we have this van der Waals complex, we can have an addition to form a carbon-carbon single bond. So we have a barrier to addition, but this barrier to addition is lower than the energy of the separated reactants, which is effectively a submerged barrier. So the reaction is essentially barrierless. Then we have an isomerization, we have a ring closure, and we have a hydrogen migration, and then we have a hydrogen loss, which eventually brings us to the naphthalene molecule. And this is really very important that we have a barrierless reaction to naphthalene formation, which also operates at low temperatures, such as 10 Kelvin in TMC1 or in Titan's atmosphere. So we also investigated now, since we essentially add a six-membered ring to an existing six-membered ring, can this be a universal pathway? For instance, on the paper, when we have bromonaphthalene, we are cleaving the carbon-bromine bond. We have the 1-naphthyl or the 2-naphthyl radical. If this reacts with vinyl acetylene, we should add another six-membered ring. We should add one six-membered ring here, here, or here. And that's what we experienced and investigated at the advanced light source. We prepared 1 and 2 naphthyl radicals in separate experiments, reacted them with vinyl acetylene, and recorded a signal at mass to charge 178 and extracted the photoionization efficiency curve and detected phenatrene and anthracene. So this also provides evidence that we can form complex aromatic structures with this Haber mechanism. The reaction mechanism is actually similar how naphthalene is formed, but more complex, as we will see here. These calculations were also done by Alex Weber. So we have once again the vinyl acetate molecule and the 1 and 2 naphthyl radical. Once again, we form van der Waals complexes in the entrance channel where the aromatic radical is directed actually to the CH2 unit of the vinyl acetylene molecule. Here are the van der Waals complexes. Now it's really important. We have two classes of addition processes. If the radical center adds to the CH2 unit, we follow the blue pathway, where the barrier to addition is lower than the energy of the separated reactants. So essentially a barrierless reaction with respect to the reactants. We form intermediates. We have, again, ring closure, hydrogen migration processes, and hydrogen elimination plus aromatization to form anthracene and phenatrene with the blue pathways effectively without barrier. So this pathway again is barrierless and it operates at low temperatures, in theory up to 0 Kelvin. So when we fill this in and expand it to the original slide with the Haka only reaction mechanism, those pathways in blue are actually barrierless. We can go from phenyl to naphthalene, we can go to phenatrene and anthracene. So this gives a very universal pathway to form aromatic systems by ring annulation at very low temperatures by the Haber mechanism. This can also be expanded to more complicated systems because this is a versatile pathway. Essentially 3 classes of aromatic systems, which are azenes, which have an essential linear arrangement of the benzene rings, phenacenes, which have a zigzag structure, and helicanes, which have actually a curved or chiral arrangement of the aromatic rings, can be formed in these processes. Those PAHs color-coded in red has been detected in our experiment. Those in blue are still currently being investigated. So this presents a really versatile pathway to add one six-membered ring at a time at very low temperatures. So this also provides evidence that these molecules should be sooner or later be observable in TMC1, for instance. So what's happening now if we have HACA and HAVA combined? So when we start with triphenylene, for instance, if we have HACA, we can make the 4+2 Bay closure to form coronane. If we have now the HAVA and we are adding 3 six-membered rings and we combine it with HACA, again, we can get circumcoronane. So essentially a combination of HACA and HAVA in deep space or even in combustion processes can form very easily two-dimensional or graphene-like nanostructures in these extreme environments. But so far, we only have investigated how we can form planar aromatic systems. Is there any way how we can introduce a 5-membered ring in these aromatic structures? So we investigated for that also under cross-molecular beam study, the reaction which came out recently of the CH radical with CH88, which is the styrene molecule. And we detected signal which is equivalent to a molecule which is formed C9H8 plus a hydrogen atom. So C9H8, it could be, of course, the indane molecule. So we also conducted a transformation from the laboratory data to the center of mass data. We extracted translation energy distribution and center of mass angular distribution. And we found evidence that based on the energy distribution and center of mass functions, we do form the indane molecule in this reaction of the CH radical with the styrene molecule. So how does the reaction pathway go to indane? So just when we look very naively from the electronic structure viewpoint and the structure of the molecules, we could see here we have a 6-membered ring in the reactant, here we have a 6-membered ring. Here we have 3 carbon atoms, here we have 2 carbon atoms. So we could think that the CH might attack the double bond, then we have cyclization. This is actually the easiest pathway, which was confirmed computationally. We have a barrierless addition of the CH radical to the carbon-carbon double bond. We form a 3-membered ring here. We have ring opening, isomerization, ring closure, and we lose a hydrogen to form the indane molecule. However, this has pathway A. So the electronic structure calculations also revealed 2 additional pathways. Naturally, CH can not only add to the carbon-carbon double bond, but it can also add to the carbon 6-membered ring. And this gives very complex reaction dynamics, which are summarized here. We have the reactants, and the carbon atoms in the reactants are color-coded for the benzene ring, for the vinyl unit, and for the carbon for the CH radical. And we have 3 pathways. And only in pathway number A, what I showed you before, are the carbon atoms of the benzene rings conserved. In all other pathways, the carbon atoms are extremely scrambled because the CH reacts actually with the benzene ring. And as a critical example, in this case, for example, pathway B, the CH is later on incorporated in the 6-membered rings, and the benzene ring is completely split up from the 6-membered rings formed to ring contraction. So these are really complex reaction dynamics, which also suggest that PAHs in space are not necessarily as stable as previously thought, because the CH radical can react without barrier and very rapidly with 6-membered rings, and also with vinyl groups at 6-membered rings. However, this pathway presents a barrierless pathway to form in cold molecular clouds and also in planetary atmospheres, which are hydrocarbon rich. So finally, we also invest reaction of the phenyl radical and dehydrocyclization processes I would like to summarize it on one slide. So the phenyl radical can have actually essentially two different pathways. We can react with a biphenyl molecule. So there we have a 4-carbon base structure, or it can react with a naphthalene structure in this PSC path where we have a 3-carbon base structure. If it goes to the naphthalene, naturally it can add to the C1 or to the C2. We form the 2-phenyl or the 1-phenyl species. So the 1-phenyl naphthalene can lose hydrogens either by photodissociation or by hydrogen abstraction. We get a radical, we have ring closure and another hydrogen loss, and we form the fluorantene. So this PAC mechanism, when we have the phenyl and the C3 base structure, essentially forms an indene substructure. On the other hand, when it reacts with the 4-carbon structure, we can see the formation of the ortho-terphenyl radical, which we also detected as an intermediate. Again, hydrogen can be lost by photodissociation or abstraction and to form the triphenylene structure. This means we are expanding the 4-carbon the base structure to essentially a naphthalene subunit in this pHs. Of course, since the phenyl radical, when it adds to aromatic structures, has a barrier, this mechanism operates only at high temperatures. So we could also combine now multiple pathways like HACA, HAVA, PAC. And this culminates in the formation of a coannuline molecule, as we have shown in pyrolytic reactor studies. So we start with the phenyl radical. The phenyl radical can form the naphthalene either by HACA or HAVA. Then by PAC, we form the 1-phenyl naphthalene, which brings us then to fluorantene, as we have shown previously on the previous slide. Then we can abstract a hydrogen atom, we get fluorantene, and we have 2 additional HACA mechanisms to essentially form coannulene. So this has been detected as a terminal product. This reaction intermediate has also been detected in the studies, and naturally also the fluorantene molecule. So by a combination of multiple reaction pathways, it's evident that coannulene molecule, which acts as a building block for the cap of the C60, can be formed in deep space. But since these pathways also involve pathways which have entrance barriers, naturally this can only happen at elevated temperatures. So the final pathway and the mechanism, these are the most complicated ones to be studied, are radical-radical reactions. They are difficult to study because we can only have very low concentrations. Otherwise, we would have undesired self-recombination. And so far, we only investigated 2 radical-radical recombination pathways. One pathway which we investigated originally was the reaction of the indenyl radical. We are generating by pyrolysis of bromoindene with the methyl radical and also with the CD3 methyl radical under controlled reaction conditions. We have multiple pathways starting from indenyl with the D3 methyl, so we could actually trace the location of the deuterium atoms and how many deuterium atoms are left in the final product. And we detected then the naphthalene molecule, actually the D2 naphthalene molecule, as evidence of this proposed reaction mechanism, that we have a radical-radical reaction between indenyl and the D3 methyl radical. Another reaction which is currently in press, which will come out in a couple of days, is a propaga-propaga self-reaction, which forms benzene, but at a much lower percentage as originally anticipated, only about 10% of benzene, whereas 90% are non-cyclic benzene, benzene isomers. So if we put everything together, we can combine it to a molecular mass growth chart. We actually can start with naphthalene and phenyl. All the pathways in blue are actually barrierless pathways, which can operate at 10K in cold molecular clouds and in Titan's atmospheres. So we have essentially the stepwise molecular mass growth process by adding 6-membered rings 1 by 1 to very complex systems, even up to chiral helicene substructures. And we also have a combination of Hacker, Haver, and PAC to form structures as complex as coanolane, which are molecular building blocks of carbon-60 caps. So we have investigated now how these 5 elementary reactions can lead to the formation of aromatic systems in the gas phase. And this has been summarized in a recent feature article in JPCA, if you like to read more details. So the next goal over the years would be to really see that we can form and find out the mechanisms how carbon-60 and carbon-70 building blocks and fullerenes can be actually formed under extreme conditions, means high temperatures and possibly at low temperatures. So, however, space is not that easy. We do not only have the gas phase, but we also have the condensed phase. And this is mostly demonstrated on Titan again, because on Titan's surface, we have large amounts of black stuff, how the astronomers or planetary science call it. And this black stuff, to be a little bit more scientific, it's an organic material of unknown origin where the infrared features suggest there are some aromatic substructures. So our goal was to see, can actually acetylene in the solid state under Titan's temperature conditions be converted by energetic galactic cosmic rays which can penetrate up to Titan's surface. And we wanted to see, just as a proof of concept, very simple aromatic structures such as benzene. So we conducted some test experiments, but this was complicated by the fact that benzene has 217 isomers. So 217 isomers, if we do tunable VOV studies, it will take forever. So the ideal choice to detect benzene molecules in condensed phase simulation experiments after their formation in the ice is actually Rampey spectroscopy, where we have a ground state, we go 2 photons omega-1 to an excited intermediate state, and then we are ionizing. And this is selectively for benzene, and we cannot ionize the remaining benzene isomers. And through this experiment, we actually condensed acetylene at 10 Kelvin, exposed it to ionizing radiation in forms of energetic electrons, then sublimed the molecules and conducted Rampey spectroscopy for different 1+1 Rampey for benzene, 1+1 for phenylacetylene, styrene, and naphthalene, and detected large quantities of aromatic structures, which up to 8 benzene rings. So the most complicated we could detect directly by Rampey is actually the phenanthene molecule. And this was done by one of our graduate students. So we also we also try to explore computationally how does this really work. And we conducted additional experiments where we selectively, just for mechanistical studies, excited only certain states of the acetylene molecule. In this case, we excited only the first excited triplet state of acetylene, which is of course formally spin forbidden. So the electronic structure calculations only for the gas phase on this slide suggests that if you have 3 acetylene molecules, if you excite one of them in this trimer to the first excited triplet state, which is here in the cis form, you have a small barrier to addition, but from there you have multiple isomerization steps. It's only downhill to actually form a triplet benzene, which can then undergo intersystem crossing in the condensed phase. However, in the real ices of acetylene, you also have matrix effects and solvation effects. And our collaborators investigated the solvation effects. And for each of those intermediates and transition states, they added acetylene molecules step by step. And it took them about a year to find this plot. So this gives actually the number of added acetylene molecules versus the relative energy of this initial transition state. Because even at 2 kilojoules per mole, at very low temperatures, we cannot overcome this transition state at Titan's low temperatures. However, as we will show, if we add 3 additional acetylene molecules on this acetylene trimer, we don't have a barrier anymore. So from 4 acetylene molecules on, we have a submerged barrier, which is about 2 to 3 kilojoules per mole, lower than the energy of the separated reactants. So essentially, once we excite the acetylene molecule to the triplet state, for instance, we have an instantaneous formation of benzene. And this was also evidenced in the large yields of benzene. When we excite molecules, for instance, to the first and second excited triplet state and to the first excited singlet state with selective photons. So I would just like to summarize quickly that I hope I could show you a little bit how aromatic systems can be formed in deep space, and that we also have different pathways to identical aromatic structures. For example, to naphthalene, we could go with the Hacker mechanism, with the Haber mechanism, with radical-radical reaction mechanisms. And also to anthracene and phenatrene, we have multiple pathways. So when it comes to modeling of formation of aromatic structures in space, in planetary atmospheres, or in combustion processes, it's really important to get really meaningful model outputs. You must have correct inputs of the models. You cannot just neglect certain pathways, because as our experiment showed, multiple pathways can go to the same pHs. Some, of course, at low temperatures. Some of them are operating only at high temperatures. So the modeling of the pHs is really not that easy, but based on our results, it should be more doable. And we should focus once again, at least in the gas phase, on these 5 elementary reactions. And hopefully in the next years, we can find out and extract additional mechanisms, how these aromatic substructures can be formed in deep space. Finally, I would like to thank the people who conducted the work. So Long did most of the experiments at the advanced light source. Alex Mabel, the electronic structure calculation, Musa collaborating with the advanced light source studies, Stan Yuk and Felix Fischer for synthesizing many of those precursors. Otherwise, the experiments would have not been possible. And thank you for listening to the 2.0 version of the talk. Thank you.
Thank you, Ralf. This went very well, and thank you for a great talk. I have a bunch of questions already lined up. First is Perry Haley. The question is, have you investigated the chirality of the helicins in your work? And before I go, can Kyle or Heather please unmute Professor Nesbitt so he can ask his question? It's a long question. Maybe you can unmute him for the next question. Thank you.
So we don't have the capability now to investigate the chirality. We do know that we form 4 helicene and 5 helicene. So the barrier for chirality for the inversion is pretty low for the 4 helicene. But of course, the higher the helicenes are, up to 6, 7, there is a plateau. At least in interstellar medium, they should be stable once they are formed. So that's all what we can say. We think we form racemic mixtures, but we don't have evidence for this. But we don't have any chiral templates or chiral reactants which promote the formation of chiral helicenes in our reactor studies so far.
Okay. So the next question is from Professor Nesbitt. Please go ahead.
So Ralf, aloha from
Hi.
Boulder.
Good morning.
Look, in your MACA mechanism, you really showed that the carbon in the methylidine basically can, in effect, move around the ring depending upon what your pathway actually is.
Yeah, this was actually reaction path B and C. I mean, Alex Mabel calculations, as you know, they are always very high class and very, really very complicated. If I had shown pathway number B and C, you would see only structures. That's why I'm summarizing it actually here on this slide.
And so the take-home message is that the carbon is essentially sort of almost labile in terms of how it can move around the ring depending upon what mechanism it goes. I'm
Correct.
wondering, is the hydrogen associated with that carbon, is it promiscuous as well? Does it remain attached to the inserted carbon? Have you done?
Yes,
Yeah.
I know what you mean. The hydrogen end sticks actually here to this carbon atom. So this doesn't actually migrate much.
Interesting. So have you done CD studies that would allow you to be able to?
Yes, we also did CD studies and we verified the reaction pathway.
Excellent. So that's quite interesting that the carbon moves around but drags the same hydrogen with it. Interesting. Thank you.
Okay, thank you. The next question is from Anonymous. What conditions were the propergel recombination experiments performed under?
Oh, we had them at different backing pressures, between inlet pressures between 100 and 400 torr. But inside the reactor we have a pressure gradient, and this will all be published in these findings. The most important thing is we had to go to very low concentration, because if we go to very high concentration, let's say higher than 1%, we get everything in our beam what we really want. Because when we form originally benzene, then the benzene can react with another C3H3. We can also form indane. It can even grow to more complex hydrocarbons. That's not what we want. Whenever we want to study the formation of aromatic systems, we want to really control the reaction. And in this case of the propargyl, we only wanted to limit us to the formation of the first ring, not to more complicated rings.
All right, thanks. Next question is from G1. You have mentioned that formation of circumcoronene through the combined Haka and Hava mechanisms. Will the circumcoronene continue growing if we want to form a very large pH, for example, 60 to 100 carbon atoms that will more likely to survive under harsh ISM environments? Are Haka and Hava mechanisms still efficient?
So
compare that to the dimerization or trimerization of medium-sized pHs.
Okay, this is a complicated question. Please keep in mind, this slide was only paper chemistry. This was an implication of the Haka and Hava. We know that triphenylene is formed. We are currently investigating how triphenylene can be converted to coronane, or on the paper it should be converted with the Haka. So we have beam time again in fall, and we are investigating the passages from triphenylene to coronane. Then we investigate stepwise coronane to this intermediate. So the other intermediates, it's very complicated to investigate this experimentally because the molecules are getting really big. But at least on the paper and based on electronic structure calculation, the Haka and Hava pathways with a Bay closure, like here or here, and with the addition of the 6-membered rings from here and here, are really versatile and they should operate.
All right. I do not see any more questions. If anyone has a question, please type that, or please ask for permission and we'll unmute you. If not, then we will thank Ralf again for our excellent talk and taking his time again, and thank all of you for joining us again this week. We will have another one of our Astrocheminars next month. That will be on, let me check the actual date. That'll be on the 9th of June. So please join us for that again. And again, thank you, Ralf. Thanks everyone for joining in. It was an excellent talk, and thanks.
Okay,
take care. Bye.